Welcome, everyone, to today's podcast, where we'll be delving into MatterGen, a groundbreaking generative model for inorganic materials design. I'm really excited to see what our experts have to say about this innovative approach that's poised to reshape the materials discovery landscape. Let's jump right in.
Thank you for having us, host. MatterGen is in essence a diffusion-based generative model that addresses the complex task of creating inorganic crystalline structures, atom types, coordinates, and the periodic lattice. It's actually the first time we've seen such a robust solution that can generate stable materials across the periodic table in one unified approach.
Absolutely. It's a two-step process. First, MatterGen is pre-trained on a large dataset of stable structures. Then it gets fine-tuned using smaller datasets for specific property constraints. The pre-training uses something called AlexMP20, which is a compilation of over 600,000 stable structures.
Right, that's the data side of it. And just to add, this approach is essential for businesses looking to innovate in, say, battery technology or carbon capture. We're not just talking about incremental improvement, but genuinely new compounds that might never have been considered before.
I'm glad you brought up the business angle, because from my perspective, when companies try to find new high-performance materials, like new types of catalysts or improved solid-state battery electrolytes, they can spend millions of dollars on trial-and-error lab work. With MatterGen, the R&D cycle can speed up dramatically.
That's phenomenal. Before we talk more about the business implications, can we break down how MatterGen actually diffuses through possible structures? The text mentions atom types, coordinates, and the lattice. That sounds, well, quite complicated.
It is. Normally, diffusion models for images or text just add noise and then learn to remove it. But for crystalline materials, there's a more specialized definition of noise because the periodic boundary conditions are tricky. So MatterGen uses a wrapped normal distribution for coordinates. Imagine atoms drifting around in fractional space, but still respecting the lattice boundaries. Meanwhile, the lattice parameters themselves are also allowed to fluctuate in size and shape.
Yes, plus we can't forget the categorical diffusion for atom types. Essentially, an atom can get masked out and then the model learns to guess which element it should be. All these bits of noise are removed in reverse by a neural network that's been trained to denoise each step. That's the generative magic right there.
And as the text highlights, the final structures after DFT relaxation are typically within 0.076 angstrom RMSD of the initial guess. That is incredible closeness to the local energy minimum, indicating these structures are extremely close to stable from the get-go.
Indeed, that's huge for practical applications because it means fewer costly DFT calculations. Let's talk real world for a second. If you're, for instance, a solar panel manufacturer searching for a novel absorber material, you can generate thousands of candidates with a matter of computational hours rather than months of guesswork.
That's a major time saver. Now, what do we mean by SUN materials, stable, unique, and novel?
So stable means we measure the energy above the convex hull and see if it's below 0.1 EVs per atom, an accepted threshold for potential synthesizability. Unique means the structure hasn't already been generated by the model in that same batch. And novel means the structure doesn't appear in a massive reference database.
Exactly. And if you look at the percentages, the text says that MatterGen yields about 78% stable structures depending on the hull reference, and around 61% of them are novel. That's basically letting you discover new crystals that might have never been tried before.
And that's significantly better than earlier generative attempts like CDVAE or diffCSP, which had lower novelty or stability rates. MatterGen's synergy between a carefully constructed diffusion process and a big training dataset gives it a leg up.
I agree with you, but there's more. MatterGen can also handle multi-element systems, a big deal in advanced materials design. Ternary or quinary compositions are absolutely crucial for modern battery cathodes, for example.
Interesting. Now, if I'm a business leader wanting to reduce my supply chain risks, maybe I want to avoid using rare earth metals, can MatterGen help me out there?
Definitely. One of the neat capabilities is that it can be fine-tuned to produce materials with a desired Herfindahl-Hirschman index, which is basically an indicator of supply chain concentration. If you want a magnet that doesn't rely on, say, neodymium, you can specifically instruct MatterGen to generate compositions with lower HHI.
Or if you want a higher bulk modulus material for superhard coatings, MatterGen can do that too. It's literally a matter, pun intended, of providing a target property, and the model's fine-tuned adapter modules do the rest.
Nice pun. But it's truly remarkable how flexible it is. A company might say, we need a novel catalyst that's stable, has these 3 specific elements, and meets a certain level of catalytic activity. Then MatterGen, combined with a property predictor, can guide you right toward promising candidates.
And it's not just hypothetical. They literally synthesized a material from MatterGen's output, TCR206. The measured property ended up being within about 20% of the target. That's a big validation that we're not just generating digital nonsense.
Wow, that is legit. Let's talk about that real-world demonstration. They targeted a high bulk modulus of 200 GPa, correct?
Yes, that's right. And after screening thousands of generated samples, they found some that were stable and feasible to make in a lab. One of them ended up being TCR206. The final experimental bulk modulus was around 158 to 169 GPa in a non-compact sample. That's actually quite close, especially for a first try.
Indeed. And if you look at the broader set, MatterGen even rediscovered 101 known materials from the ICSD that it had never been trained on. So it's showing it can spontaneously produce real, experimentally verified structures.
You know, it's almost like the model is not just a generation tool, but a discovery engine. I recall reading that it even found a bunch of materials on the convex hull in well-explored ternary systems that random structure search missed.
Yeah, I love that part. I mean, RSS can be so computationally expensive. With MatterGen, you generate fewer structures but get more hits. That's huge for companies strapped for CPU or HPC time.
Let's pivot to business strategy for a moment. Suppose we run a big energy storage firm wanting to find new high-voltage cathodes. We do, say, tens of thousands of structure generations, then filter out the stable ones, then do a final DFT check. How does that compare cost-wise to more traditional methods?
Confidently, it can be orders of magnitude cheaper in terms of total DFT calls. Traditional random searching might take hundreds of thousands of calculations to explore a large design space, whereas MatterGen directly steers you to the stable region. That alone can save months of HPC time.
And HPC time is not exactly cheap these days. If you're on the cloud, you might be seeing that credit card bill and thinking, well, maybe I should have used a generative model.
That's definitely a conversation I've had. So from a business perspective, you can tie it all together. Less HPC cost, faster time to market, and a bigger chance of discovering that unicorn material.
Precisely. Another angle is the environmental aspect. By drastically cutting down on experimental trial and error, we reduce chemical waste and lower the carbon footprint of labs. That's an increasingly important selling point.
Great point. Now let's talk about combining multiple property constraints. The text references magnets with both high magnetic density and a low HHI. How exactly do they do that?
They effectively train MatterGen to produce structures with a magnetization target, say 0.20 Oxmers-3, while also restricting the elemental composition so that the HHI remains under 1500. Classifier-free guidance helps push the generation in that direction.
That's right. And after some iterations, the distribution shifts toward corners of the element space that are lower risk but still have the potential for strong magnetism. They basically cut out those supply-risky elements like cobalt or gadolinium.
I see that as a huge plus for the automotive or wind energy industries that rely heavily on permanent magnets. If there's a trade ban or a shortage, you're in trouble if you rely solely on rare earths. This technology can find alternatives.
I agree with you. And on top of that, let's not forget that MatterGen has direct synergy with machine learning force fields, MLFFs. So we can do rapid pre-checks before even running DFT on everything. That multi-stage approach ensures we're weeding out the obviously unstable or poor candidate structures.
That's so interesting. Are there any limitations or things to watch out for?
Well, the authors note that the model tends to produce more low-symmetry structures, like P1. That might be fixable with a better approach to the lattice portion of the diffusion, or with more training data that emphasizes higher symmetries.
Also, we have to remember that generating stable crystals is just the first step. Real deployment might demand we check mechanical properties, doping, temperature stability, plus experimental feasibility. MatterGen is a great jumpstart, but there's still more steps after generation.
Right, in real labs, you also have to worry about phases forming or synergy with existing manufacturing lines. But if we can come in with a short list of, say, 10 brand new candidate materials rather than 10,000, that's a massive improvement already.
Definitely. And from a strategic standpoint, those shortlists can feed into lifecycle analyses, cost models, and regulatory approvals. No more shotgun approach.
I can see how that's a game changer. Let's do a quick hypothetical scenario. A major company wants to create a new semiconductor for advanced computing, something with a specific band gap and a certain mechanical resilience. Would MatterGen have them covered?
Yes, indeed. They'd simply fine-tune MatterGen on a labeled dataset of band gaps, like they did with 42,000 structures for the 3.0 EV target, and also supply mechanical property labels if needed. Then, using classifier-free guidance, the model can propose materials that meet both criteria.
Right? It's that same principle. And in many ways, that's how you do it for carbon capture materials, new thermoelectrics, or even superconductors. The approach is super generalizable.
I recall there's a mention in the text about extended applications to metal organic frameworks or catalytic surfaces in the future. That's definitely on the horizon if they expand the data and adapt the architecture.
Absolutely. There's a lot of potential synergy with other AI for science endeavors. For instance, if we integrate MatterGen with large language models that interpret experimental papers, we could further refine the search.
That synergy is always fascinating. By the way, have you folks ever had a model generate something so bizarre it made you wonder if the AI was playing a prank?
We did see a structure that was basically a crystal spaghetti situation in an early trial, atoms all over the place in a big messy cluster. But with enough training data and the right diffusion process, those comedic outputs become very rare.
Every AI has its rebellious teenage phase. We just let it go and learn from it.
For sure. But after we hammered out the bugs, the results speak for themselves, like generating thousands of stable novel crystals that pass DFT checks with ease.
I agree wholeheartedly. That's the highlight. You can trust these generated samples enough that they don't turn into computational sinkholes for your HPC cluster.
So folks, if I were a prospective CEO listening in, I might be thinking, wow, this is so advanced but maybe too technical for our teams. Is there any user-friendly UI or pipeline that can help with MatterGen?
Well, the typical setup involves hooking MatterGen's generative output to a pre-relaxation with an ML force field, something like MatterSim. Then you do final DFT runs. That can be integrated into standard materials pipelines. And we're seeing more user-friendly front ends being developed, particularly in open source communities.
Exactly. And the big players like Microsoft are investing in these AI for science toolkits. So it's likely we'll see robust software solutions that let you pick your property constraints from a menu.
Then you just press generate and you're off to the races. For large corporations with dedicated HPC resources, it'll be a huge productivity booster.
Also, for startups trying to disrupt industries, it levels the playing field. They can get advanced materials R&D done without a huge lab overhead.
That's a big promise for sure. Let's circle back to the text conclusion. It suggests that MatterGen might be just the start of a new era in materials design, akin to how generative models revolutionized images. Do we all agree with that?
I do. We've seen how stable diffusion or ChatGPT changed natural language or image generation. Now MatterGen is bringing that revolution to crystallography, automating a big chunk of the materials discovery process.
I think we'll see an ecosystem grow around it, with specialized fine-tuned versions for batteries, semiconductors, catalysis, quantum computing materials, you name it.
This is just the beginning. As the data and the model architecture improve, we might see leaps in accuracy and new ways to incorporate experimental feedback.
Indeed, next-generation solutions might incorporate partial experimental results, advanced property predictions, and so forth. It's a rapidly evolving field.
Well, folks, this has been super enlightening. In about half an hour, we've covered the fundamentals of MatterGen, its technical underpinnings, the massive potential for businesses, and even a slice of humor about rebellious AI. Are there any last parting words before we wrap up?
Just that I'd encourage businesses and researchers to give these generative models a try. Start with something manageable, maybe a ternary system, and see the magic unfold.
Definitely. And keep an eye out for expansions of MatterGen's capabilities, like more complex materials classes. It's an exciting time to be in materials science.
I agree wholeheartedly. We're about to witness a transformation of our field, and everyone with even a mild interest should jump on board.
Indeed. Thanks for having us, host, and letting us share the story of MatterGen.
The pleasure is mine. Thanks to all our experts for their deep insights, humor, and clarity. And thanks to all our listeners for tuning in. Until next time, stay curious and keep innovating.